So the final presentation is going to be given by Wenhu, who is another master student from Wuhan University, and he will tell us about how to find IoT or vulnerabilities in IoT firmware. Go ahead.
Thank you. Hello, everyone. My name is Sun Wenhou, the presenter today. And this paper is mainly authored by Zicong Gao, and collaborators include Chao Zhang, Hangtian Liu, me, and so on. And we are from Information Engineering University and Tsinghua University. I'm glad to present our research here, which is titled Faster and Better Detecting Vulnerabilities in Linux-based IoT Firmware with Optimized Region Definition Analysis. As is known now, the ecosystem of IoT devices has experienced phenomenal growth in recent years. The interconnected nature of IoT devices has provided us with convenience and innovation, but also increased the risk of being hacked. The network of devices, such as routers, webcams, and firewalls, are the most commonly attacked IoT devices. Vulnerabilities, especially taint-style vulnerabilities, are one of the fundamental security threats to IoT devices. The common threat model can be described as a client-server model. A user, or to say attacker, access the target over network and send HTTP request to device. The data is first passed by a web service program in the backend. Then the data is propagated to a handler program that loads some library codes and operates the device. Up to now, many solutions to detect taint-style vulnerabilities in IoT devices have been proposed, including dynamic solutions and static solutions. Fuzzing has been popular, but for firmware, it requires analysts to tailor emulation environment. And static solutions do not require emulators support and could be applied to a large-scale firmware analysis. And several static taint-style analysis works have been proposed, but they still have some limitations. Like sometimes they will miss potential source points and sink points. I will show an example. Let's consider the state-of-the-art static taint analysis solutions, SaTC and KARONTE. They failed to alert the vulnerability in this figure. In this example, source points in blue text are located in the left bottom function, but this function is only referenced by a two-layer function table and only indirectly invoked indirectly. So existing works all fail to identify to this function and will not include this function in their constructed control flow graph. That is the root reason for failing to identify these sources points. As a conclusion, an incomplete control flow graph is a major reason why the source and sink points are usually lost in analysis. And someone may ask, why don't you just make improvements on control flow building on SOTA works? Yes, but SOTA works, they all perform taint analysis based on a symbolic execution. And simply enlarging the analysis scope only leads to higher time consuming, which is a nature of symbolic execution. For example, SaTC costs about half an hour to 30 hours on each sample. And when the library codes are included in the analysis, the time will increase by 2 or 3 times. And symbolic execution also faces the problems such as state explosion, path explosion, and constraint solving complexity, so making it not quite practicable in real world. So more often than not, we think static analysis should be fast and productive. So we are motivated to find the faster taint tracking scheme. Our intuition is to replace expensive symbolic execution by chip data flow analysis. So we examined a classic technique, which is reaching definition analysis. Its definition is the definition D of a variable V at the program P, which is a point Q if there is a path from P to Q such that D is not killed along that path. You can see that reaching definition analysis is similar to taint analysis, which is a definition of the taint variable V at the source P, which is sync Q if there is a path such that D is not killed. So let's turn back to our motivation example. If we apply our reaching definition-based analysis, we could see definitions of taint variable, type, and event as source code 5 and 8. They are assigned by web's getWhere, this function. They all reaches the function here, sync function here in system. Those two variables are related to another variable V74 in the right bottom figure, which triggers a vulnerability rule indicating a vulnerability. However, when we apply our reaching definition analysis on real-world devices, it still faces 3 problems. First problem is comprehensive control flow graph recovery. Current control flow graph construction methods have problems in identifying indirectly invoked functions, thus they will miss potential source or sync points. A second problem is precise source point identification. Manually specifying source functions requires expert knowledge and customization, while existing works like SaTC proposes matching back-end key strings with front-end web pages and scripts to identify potential inputs from users. Its method is not accurate enough to find as many sources as possible. Third, although reaching definition analysis is lightweight, it still faces the problem of path explosion. So to deal with the above challenges, making taint analysis faster and better, we propose HermeScan. At the high level, this is its overview, and it features in 3 key steps. First, it recovers function information to carry out an enhanced control flow graph recovery to build a more comprehensive control flow graph. Next, HermeScan uses fuzzy matching to locate candidate source functions through the shared strings of the front and back ends. Then it picks out functions representing user input from the candidate and 10 proper parameters, which avoids false positives caused by overtaint. Then the efficient data flow analysis performs a lightweight, context-sensitive, on-demand reaching definition analysis along each path. Okay, next page. We enhance existing control flow graph recovery solutions from the perspective of practicability. First, HermeScan scans the full disassembled binary to recognize function boundaries by matching the features of the function prologue. Besides, when a section header table in an ELF has been stripped, HermeScan still identifies the address of a symbol table by parsing metadata from a PT dynamic segment. At the same time, HermeScan not only established the control flow graph for binary, but also for library codes and connecting those graphs by matching symbolic names. And in source input identification, HermeScan first proposed a fuzzy matching strategy to discover more candidate source points. Our fuzzy matching strategy takes into account both word form similarity and semantic similarity. To measure word form similarity, the normalized added distance is used. And for semantic similarity, HermeScan utilized the transformer's BERT model to calculate the cosine similarity of string embeddings. So semantic similarities help to capture the hidden associations of strings. Finally, HermeScan recognizes functions referencing these strings as candidate source functions, which are likely to parse external inputs. Next, we conduct a candidate function checking to remove misrecognized candidate functions and mark correct function arguments and return values as taint sources. HermeScan checks whether the parameters would receive values from external input and check whether the return value would be used by following codes. HermeScan proposes a unique taint tracking scheme according to 3 principles. The first principle is lightweight. We leverage rich definition-based taint tracking instead of heavy symbolic execution. And for the input variable of interest, we build a depth use graph, where each node represents a variable depth, and each edge indicates a use after depth. The second principle is context sensitive, and the third principle is on demand. Specifically, we only step in functions with tainted parameters for interprocedural analysis, and we'll apply summaries of common library functions. And we take the following example to illustrate our analysis. In this example, getEnv is identified as a source input function. So variable v4 is identified as a source point. The variable is propagated to the blue box functions, up-down services, and func2. So those functions, so our taint tracking engine also steps in these functions. But for those 2 functions, they are not analyzed because their parameters are not tainted. Finally, when we encounter some library functions, we'll apply the summary of string copy. And it fills the stack variable above with the value pointed by taint variable A1. HermeScan designs a path merging strategy to identify and merge paths that are analyzed too many times. The strategy leverages the path insensitive feature of rich definition analysis and employs 2 schemes, multi-source taint and multi-sync observation based on control flow irritability. For the function that contains multiple input source points, we could taint each point with a different label at the same time and track the taint propagation in one pass. And for multi-sync observations, all reachable things in the same call graphs are covered in one rich definition analysis. By analyzing so many sources and sync pairs at a time, HermeScan avoids many redundant analysis procedures. So how does our solutions perform? The evaluation first compared the vulnerability discovery capabilities of HermeScan and other SOTA tools. Then an ablation experiment was conducted on 3 key techniques of HermeScan to evaluate the effectiveness. For the data set, we selected 30 latest firmware samples from 8 manufacturers covering 4 popular embedded architectures as our 0-day dataset. And we also set up a larger N-day dataset, which is used for large-scale testing to verify the effectiveness of our method. We first compare the number of vulnerabilities discovered by HermeScan and SaTC and KARONTE. HermeScan receives 297 alerts with 156 vulnerabilities, which is far more than SaTC and KARONTE. For accuracy, HermeScan outperforms SaTC in true positive rate by 39 percentage points. And for efficiency, HermeScan is 7.5 times faster than SaTC and 3.8 times faster than KARONTE. The result demonstrates that by ensuring efficient source points to explore, HermeScan dramatically decrease the analysis time consuming by using a lightweight on-demand data flow analysis to achieve taint tracking. We also experimented different combinations of control flow graph enhancement to figure out the contribution of each option. And in this figure, we tested different strategies, including identifying function boundaries, recurring symbolic names, and the shared library control flow graph. And evaluation results show that all these strategies all remarkably help discover more vulnerabilities as a result of finding more function to analyze. As for input source identification, the checking for the source candidate functions reduced the false positives of identified vulnerabilities by 18% on a 0-day dataset. And enabling fuzzing match strategies can help us find about 63 more true positive instances. Thus, the input source identification effectively help us reduce more false positives and false negatives. And the path merging strategy is also very prevalent. And the path merging and the 22 of 30 samples merge more than 90% of the paths, which is a significant it's a significant improvement on its efficiency. So in conclusion, we present a lightweight region definition analysis solution, HermeScan, to perform taint-style analysis on IoT firmware. And it helped us discover those 87 0-day vulnerabilities in real world, and 69 of them have been assigned with CVE IDs. We also built 2 sets of firmware samples and comprehensively evaluate the performance of existing tools. So that is all for my presentation. Thank you for listening, and questions are welcome.
I thank the speaker. All right. Your name and affiliation, please, and then your question.
Eddie Treu from KU Leuven. Attackers can also misuse taint analysis to find vulnerabilities in systems. Do you have any mitigations in your approach that are novel with respect to mitigating access to attackers to your tool?
So your question is, how do we mitigate these vulnerabilities?
No, how to prevent that attackers use your tool?
Sorry, I can't quite hear clearly here.
How to prevent that malicious attackers use your tool?
How to prevent these vulnerabilities?
No, how to prevent that malicious attackers use your tool?
This work focuses on how to discover vulnerabilities so that the manufacturers can fix these vulnerabilities in time so that they won't be exploited by attackers. Okay.
Hi, Andrea Continella, University of Twente. Thanks for the talk. Quick question. If I understood correctly, you're replacing symbolic execution with region definition analysis. Does this mean that your approach cannot track constraints on the tainted data?
Pardon for the question?
Yeah, so by using region definition analysis,
yes,
can you track constraints on the tainted data? Like, can you check when tainted data reaches a sink, whether there are any constraints on the let's say length of the buffer that is being used or something like that?
Yes, we can put taint tags on strings and track how they be used by different functions.
Okay, so you can then also compute constraints when the data goes through processing functions. Is that what you're saying?
Taint won't be dealt precisely in different strings functions, but we'll track how taint flow across different strings.
All right, thanks.
Okay, thank you.
One more question
Hey.
there.
Hey, Lucas Drazel, UC Santa Barbara. I had a quick question. So in your motivating example, you kind of showed that one of the biggest issues that these existing analyses had were indirect calls and indirect function, like indirect jumps. But I couldn't see from your presentation, did you do anything to address that, or did you more focus on expanding the set of functions that were analyzed in total? Does your work make any improvement on the indirect call resolution at all?
Not. We aim to find more functions and integrate more of them into our control flow graph. But our solution did not directly help identifying more indirect calls. Instead, we found more functions. That is our approach.
Got it. Thank you.
Okay.
All right. Then let's thank our speaker again.